Podcasting from Lund, Sweden, home to the vicious sausage battle between the Lundamelle and the Lundaknake, and one of the most advanced laboratories in the world, Max 4. This is Intronauts, bringing you inside the Max 4 facility, where you get to meet some of the greatest minds and the explorers of tomorrow. I am your host, Toril Kornfeldt.
And I'm the co-host, Laura Raster, and I'm really excited because today we get to talk about the inner workings of the facility.
And we're meeting Stephen Molloy, Mirjam, Lindberg, and Anne Terry. So we're starting with you, Stephen.
Hi.
Hi. What is your title? What do you do here at Max?
I am the head of accelerator operations. So my group is in charge of running the 3 accelerators that we have.
So you are an engineer and you're working with making the machinery work here.
Yeah, I'm trained as a physicist. My PhD is in physics, but I work as an engineer, just like you said, and I have a team of about 12 people who work 24/7 just to keep the 3 accelerators that we have running at whatever values that we've promised for our users.
It sounds like a really big job.
It's kind of exciting. It's sometimes a little stressful, especially when things go wrong. That's when all the fun is, but that's when all the stress is. We've got to keep the machines running for as much as possible. It's about 5,000 hours a year for each of the 3 accelerators. And we are aiming to get about 97% reliability. So the machines actually work for more than 97% of those 5,000 hours. So when something happens, you got to scurry and work pretty hard to fix it before, the clock is ticking, right?
I think that's a better percentage than my phone has.
It could well be. It's a number that we're really proud of here at Max 4.
That's nice. Can you give me just sort of an overview of the facility for someone who's here for the first time or haven't seen it?
So when you first come here, there's the big ring that you see immediately. It kind of looks like a UFO has landed in Skåne. And that's the big accelerator. It's kind of the flagship accelerator. And then we have a smaller ring that's, so the big ring is about 500 meters around. The small ring is a little bit less than 100 meters around. And then lastly, we've got the linear accelerator. So it's just a straight line, not a circle. And it is used to fill up the rings, but it's also got its own bunch of users. So we've got to keep all 3 accelerators running constantly 24/7.
So what do you actually produce? What do you make?
Well, when you make the electrons move in a specific way, they emit very focused, coherent, bright pulses of X-rays that then go down a beamline and are shone onto different samples. The expert here is going to talk in a moment. And different experiments are done. So really what Max 4 is doing is providing light to users to enable science.
So what about the very basic components that keeps it running? What makes it all work?
So electrons will move in a straight line. So to make them move in a circle, we have a lot of magnets installed. These magnets just apply a force to the electron beam. And that force just keeps the beam turning around in a circle. But because the electrons all have the same charge, those charges want to push each other apart and want to make the beam get bigger and bigger and bigger and less bright. So then we have a lot of other magnets that are there in a specific configuration in order to keep the beam tightly focused so that the beam is nice and small and compact and to help the brightness of the X-ray beam as seen by the users. To give the beam its energy, that's kind of the last step in this, is that we use what's called RF power. This is very similar to a microwave oven in your kitchen, but each one that we have is about 100 times more powerful than the one in your kitchen. So it's about 100 times more powerful than the one in your kitchen, and we've got 6 of those running constantly. And they just keep pushing the electrons around, keep maintaining the energy at the right level to replace any energy lost for the X-ray beams. And then lastly, we have the vacuum system. The electrons won't move through air, so we have to have a vacuum that's something like 14 orders of magnitude lower pressure than the air in this room right now.
As far as the magnetic fields that you describe, is that really what makes Max 4 unique?
Somewhat, yes. So the thing that makes us unique is how we lay out those magnetic fields in a way that applies very, very tight constraints to the behavior of the electron bunch as it goes through so that it stays very small and very well controlled. And this was the big advance that makes MAX 4 the brightest in the world.
So we were talking earlier to Mikael Eriksson about how a lot of people didn't even think a facility like this could exist. So what has been the real difficulty in building it?
Yeah, that's exactly right. When you do the physics calculations, you can see that it works. But then when you do the engineering calculations, you can see that it's very, very tight tolerances, that you really have to align things to the level of 100 microns, and that you have to get these fields exactly at the right level to within some very small tolerance. And what the wider community believed was that if we didn't achieve these tolerances, which they said we probably couldn't, then we will have a ring that could just not store the beam for long enough, or that will have nowhere near the promised properties, or that we couldn't even get beam into. It just wouldn't work at all. As Mikael said, it was the engineering, building these massive blocks of different magnets all in one piece of iron and machining them to these precise tolerances, lowering them into the machine, getting the machine thermally stable, and getting all of this exactly right was very, very hard. And even today, I've done measurements myself where I can see a change in the length of the accelerator between summer and winter, because of just the annual cycle of heating and cooling. And it changes in length by a few hundred microns, and we can measure that. It's very sensitive. So that's over 500 meters. You can measure a change in length that's that small. And that was the big success of MAX 4, was realizing those engineering tolerances.
Does the soil and the land sort of affect the building as well?
Actually, a little, yeah. So, I mean, this land was just green fields, and then now we've put this enormous facility on top of it, and it will slowly settle, and it will compress the ground to different levels in different places, and different parts of the ground can take different compression. So the machine will slowly settle down, but not just in a nice flat way. It'll start to get a bit crooked, but remember, we're talking about the level of 100 to maybe 500 microns. Up to half a millimeter is huge for a misalignment here. But that can happen, and we've seen that happening. Slowly over the course of a year or so, we see these small changes where we're having to change the magnets that steer the beam a little bit, and a little bit more, and a little bit more to take account of this. And so what we do is, after a year or 2 years of this, it'll slow down with time, of course, but after a couple of years, we send in an alignment team who make these very precise laser-based measurements of where everything is and how far is it away from where it should be. And then they'll go in and they'll adjust these things with very precision equipment to adjust it to we're talking about, a fraction of a human hair. That's the level of the adjustments that they're making.
So I guess even despite all of this hard work, occasionally things go wrong.
Yeah. I guess I shouldn't say it, but it's one of the more fun parts of my job is when things go wrong. Apologies to the users. Yeah. And sometimes it's very simple. A power supply is not responding, so we fix the power supply, and this takes 20 minutes or less, and it works again. Sometimes it's very, very big. We had a large network outage about a year and a half ago, where the technical network just totally stopped working. So none of our devices could communicate with each other, so everything switches off. It's very fail-safe. So when a failure like this, everything switches off. And then it was just the work of, a day and a half of everybody scurrying around, trying to bring everything back together and trying to get everything back on its feet. Stuff goes wrong, yeah.
I mean, with a situation like that, who do you call besides, of course, your team?
Everybody. In a situation like that where everything's going wrong, pretty much the entire lab will be involved at some stage. Everybody's system is affected. And, people worked long days. We got everything working, and the interruption was a day and a half or so, and it could have been much, much more. So a lot of people working very hard really helped.
So a lot of people working very hard to sort of keep all of this structure functioning, and now we're going to talk to a few of the people who are a bit further down the line. So we have Mirjam Lindberg and Anne Terry. So Mirjam, do you remember this episode when things shut off for a while?
Yes, I do. I mean, that is a very high impact kind of thing to happen. We have to stop all other work that is going on and help out, of course, and get everything up and running again.
So do you also think it's kind of a fun part of the job when these things
It's
happen?
exciting, I would say. It's fun when it all comes together again at the end,
Yeah. So Mirjam, what is your title? What do you do here at Max4?
So I'm a team leader in the controls group. I am an engineer. I work mostly with software development, and now I'm coordinating controls efforts. So our group is responsible for developing and integrating the hardware and software that is needed to make everything work in the accelerator. So, for example, the magnetic fields, to be able to apply those to the magnets, we have the power supplies, so we need to be able to control those. So we have built the software that controls the power supplies, and then on top of that, there is even more logic needed to actually calculate and tune those fields. So there we work in close collaboration with the accelerator people, with Stephen's group.
So it sounds like you have a lot of different areas that you're covering to help maintain the facility. If you look at some of the biggest challenges you feel like you have, maybe on a daily basis or...
Yeah, you're right. I mean, our group has a lot of different areas that we are responsible. I mean, there is the network and the software, as I mentioned, and so on. Big challenges there is, I mean, since we're building things that are very specific and specialized, we have to be able to understand how those things are supposed to work. And we are not physicists, most of us, so we need to be able to understand the language of the physicists to see what is really needed. They might have a very clear idea of what they want to do, but we have to translate that idea into the reality. And then that is not always a simple thing to understand.
With all the different types of scientific work taking place, down in the beamlines, for example, with Anne Terry, can you describe for us a bit, just in the most general terms, what is a beamline? What happens there?
So what we describe as a beamline is we take not the electron beam, which Stephen's group produced, but we take the photon beam, so this the light beam, the X-ray beam, and we direct those onto samples. So we have this whole series of optical elements which tune that beam. It might change the wavelength, it might change the size of the beam, things like that, so that the conditions are right for the type of experiment that we want to do. So every beamline, as Mirjam's just said, is unique. No two look exactly the same, and all the techniques that each one does is different, and that means some might explore the shape or the size or the structure within a material. Some might explore what's happening within the material, the interactions and how they change.
So it's kind of like rays going out from the central ring of the structure.
Yes, so the rays do come out straight from the source. And yes, each beamline therefore is straight. So this is why you can think of it as a ray of light, a beam of light going forward.
So Anne, what is your title exactly, and what is your role here?
So I'm the manager for the diffraction and scattering group. And so I have a slightly different role perhaps to both Stephen and Mirjam, in that in my group I have a series of beamlines, so 4 or 5 beamlines in the group, which all have their own expertise, and they are all world leading at what they do. And so I'm there to help sort of coordinate some of the structure and the management that's needed for them to do their job. So I don't direct what they do, they lead their own work, but I'm there to try and help that things that could get in the way don't get in the way.
So it's a really nice sort of streamline here of like getting the facility to work and then having the software that is needed to make everything work, and then out into the beamline.
Yeah.
What is the next step when it comes to the beamlines? Because that is really a work in progress, isn't it?
Yeah. So as Stephen said, we have a number of beamlines already working that are bringing users in. And as you sort of alluded to, it doesn't just stop as soon as we open a beamline. The beamlines are being brought up with sort of initial capability, and we're constantly advancing that and trying to improve that. At the same time, we're still building yet more beamlines. And so the one that I specifically work on, we're just coming into the point where we can start to bring users in and start to make the first experiments and understand if what we designed all those years ago is actually working and coming up to specification. Beamlines that have already been operating for a couple of years, they're already thinking of upgrades and things they need to change to improve and extra capability they need to bring in. And so that's constantly evolving. And equally, the science itself that we try and address, that is also evolving. Over a short period from when we started initial design work and getting the money to build these beamlines, the science that we need to address or need to help users do has also moved forward. And so that's also another challenge that we have to do to
So how many beamlines do you have now, and how many do you plan to have in the future?
So actually in user operation in my group at the moment, we have just one beamline. We have two which are coming into what we call commissioning. This is where they're making their initial tests and sort of checking what they've built is working. And then one that's really at the initial building phase. So we're just building the hutches. So these are where the experiments take place. And then we have one we're still raising the funds to actually build.
Oh, I was going to say, I think there are 13 who are across the whole facility. There are 13 who are making use of the light generator.
Yes.
And then I think the plan for Max 4 in total is 16. There are funded 16.
16 are funded. A 17th is a possible, and that's what we're looking at. But we actually have plans for more, and we could build more. It's just what we need now, I think, is to really show that what we've built is working. So yes, we know the accelerators are working and are really leading state-of-the-art accelerators. What we need is to make sure the beamlines are also performing at the right level.
Yeah. So between the three of you, I think perhaps Mirjam's, your role is a bit more of the abstract and sort of making sure everything works along the way. What part of making all of this work do you find the most exciting? What is the thing that makes you really happy with this job?
Well, it is a very fun job to do, for sure. And it's very varied. All of these different beamlines present different challenges. We really enjoy working together with the scientists. And when we can see that an experiment is successful and that the scientists will get the data that they need, that feels really good. And on the way getting there, we can have many frustrations and misunderstandings. But during the development, each piece that falls in place and you gain more and more understanding, that's very satisfying.
Yeah. Are there any specific projects that you're working on right now that you're especially excited about?
So right now we have a beamline that's going to go into commissioning. It's the Cossacks beamline, and they have many different new types of equipment that we have not been working with before. That's very interesting. We try always to do as standard solutions as we can to make maintenance and stability easier. But then when you finally build the beamline, you will have to do some new exciting things. And that's where we are right now. So that's fun.
So what kind of things will this beamline be able to do?
So it's actually the beamline that I work on.
Right.
So what we will study is ensembles of atoms and molecules. So we are what's called a small angle scattering beamline. But that means we study large things. And when I say large, I mean less than a micron in size, so still less than the thickness of a human hair, if we use that analogy. And we study the size and shape of these ensembles of molecules. So typical application might be we want to look at how to deliver a drug to the body, and we might want to try and encapsulate that drug, and we would look at the shape of that encapsulation and where the drug is within that. We might look at nanoparticles and how they are organized. What we do, the technique is quite simple, but we spend a lot of time changing the conditions that the sample is under. So we might change the temperature, the pressure, we might flow the samples and try and understand what happens there. And what is really unique and will be world leading is because the accelerator delivers this highly coherent beam, X-ray beam, we're going to try and use that coherence to try and understand some of the interactions and the the fluctuations which occur within a sample, and that will be quite new.
And when this new beamline, the planning and everything that's been going on for years and years, how does it feel now that you're nearing completion?
I mean, obviously there's some trepidation as to whether everything's going to work. There's a lot of components to bring together to get everything there at the right time, in the right condition. This, as Mirjam said, these things are quite unique, some of the things that we've dreamt up. And so it's trying to get everything there. And so, yes, there are some nerves, obviously, but of course, a lot of excitement. We've been waiting for this for a long time.
Mirjam and Stephen, how do you feel about the fact that it's just about to open, something that you've also worked on? How do you feel?
I feel very happy. I mean, it's really good to see that all the hard work pays off. And also, as on every beamline, it's always fun when you collaborate with new people and you get to realize something really cool.
It's great, and from my point of view, because we already have 5 beamlines running on this accelerator, it feels like a new member of the family coming in.
Kind of like a kid, I guess, that goes off to school. So all of these different beamlines have these interesting names. Who gets to name them?
So that's actually the scientists when they start to dream up what they would like to build. And this is something which it takes a lot of years to get the money together and everything in order to even start designing. That's where they think of a name. And so a lot of the beamlines here at Max 4 have the name Max. We didn't. We're co-SAX, so co for coherent, but SAX is our technique. And so that's why we went for that name.
There's some others who are based on their funders.
Yeah.
So Danmarks.
Yep.
Dan from Denmark. There's Finest beams, and Finest is Finland and Estonia.
Yeah. There's one, Balder.
Yes.
And my favorite, the hippie beamline.
Yeah.
The hippies, yeah.
A hippie beamline. Is there kind of like do the beamlines develop slightly different cultures? So is there like a small internal culture for each beamline?
You do have, because of the way in which how you recruit the people, the teams that you build, the way in which the beamline works and serves the user community and things like that. That can be different depending on the types of techniques. Some of our beamlines, the measurements are so fast that the user team might only be here for 4 hours to make their measurements. Others, it will be 2 or 3 days just setting up, and then the team are there for a week. So because of that, you do end up with a different culture on each beamline.
Yeah.
And we're also different. So some are chemists, some are physicists, some are biologists. So that also changes.
Thank you so much, Mirjam, Anne, and Stephen. It's been really amazing to have you here. I just have one final question. How are you going to celebrate when you open this new beamline?
So we do open champagne. And non-alcoholic champagne as well.
Of course.
Thanks a million for listening to Intronauts with me, Toril Kornfeldt, and Laura Rasta. And if you like the show, please leave us a review on iTunes.
And don't forget to tune in for our next episode when we talk to scientists Uwe Müller and Karina Thornell about some of the projects they're working on and how they might end up improving the world that we live in.